Greetings YouTube. Today we're doing problem 35, search, insert, position. Now this problem was given by Amazon in a coding interview and it is based on binary search. So let's read the problem and figure out a solution. Given a sorted array of distinct integers and a target value, return the index if the target is found. If it is not, return the index where it would be if it were inserted in order. And we must write an algorithm with log n runtime complexity. Now, the first thing that you need to notice is this log n. This should scream, even though not 100% of the time, but you should be very, very familiar with binary search. So this is a problem that, this is an algorithm that is going to be found in a variety of problems. And it is very famous. And it shows you that you have a clear understanding of what is a log n runtime complexity. Once again, if you don't know where to start, always ask for any related topics, and here you can see array and a binary search, and the interviewer might actually say that you should be aiming at figuring out an algorithm based on binary search. Now, very quick, before we actually start analyzing the problem, binary search is based, and it is called binary because we're always dividing the set by 2. Now I'm going to write here this thing out. So I'm going to write 1, 3, 5, 6, and I'm going to have a target that is going to be equal to the number 5. So let's say that I want to find 5 in this array, and that's pretty much what I need to do. I'm going to find the middle of the array, and I'm going to take it. So that's going to be 3. Keep in mind that this only works in a sorted array, and that is why before we are actually performing binary search, we need to have a sorted collection. Now, if 3 is less than 5, this means that everything on the right side of 3 is something that I should be taking a look at, meaning that this here are going to be valid candidates. And if the number 5 here, the target, is going to be less than 3, for example, we're going to be searching for, I don't know how to delete that, but let's say that I'm going to be searching for the number 2. 2 is less than 3. So everything here is going to be valid candidate. Let's say here. This is going to be everything that we're going to be searching for when we're looking for 2. And that is why we're calling it binary search. Each and every single time we're actually going to check if the middle of the elements, the new elements that we're going to have, so here we're going to have 5 and 6, are these elements going to be equal, less, or smaller than the target that we're going to be searching for? If they're smaller, then we're going to look to the left. If they're bigger, then we're going to look to the right. And that is how we're actually going to be performing the binary search. So let's actually code it up. Now, in order for you to perform this binary algorithmic, right, to each and every time to divide by 2 and making the set smaller, what we need to do is we need to create a low pointer, or just a low value that's going to be equal to the start. So low is going to be equal to the 0 index, and high is going to be equal to the final index. If I say low plus high divided by 2, this is going to give me the middle index of this set, meaning that this, for example, is going to give me 3 here. Now, one thing that is very important, for the last very important thing to note, is that if I have low plus high divided by 2, both of them, this might resolve in an int overflow, which is something that a good friend of mine had mentioned. Now, I'm not going to dive into the idea here because it's way beyond the scope of this problem, since in this problem we're not going to have something so sophisticated. But let's say that low is an int max value, meaning 2147 and whatever the max int number is. And if I add even 1 to it, it means that I'm going to have an exception here. So that is something to note, but we're going to look at it in a different video. Now let's go with the high, and I'm going to say nums length -1. Keep in mind, once again, I want the low to be equal to the first index and high to be equal to the last. So I'm able to find the middle ones. An exit loop should be low is less or equal than high, meaning that if I have found if I haven't found anything yet and low is here and high is going to be equal to it, then just break the loop, because I have already been searching through the whole collection and I haven't found anything. So there's no need for me to keep going, because otherwise I'm just going to have an infinite loop. Now I'm going to create the middle value that I have been talking about, and this is going to be equal to low plus high divided by 2. All right. The first thing that I do want to note is, for example, if I have the numbers 1, 2, 3, 5, 6, and I'm looking for the target 3, the middle element here is going to be exactly this. It's going to be exactly 3. So I'm going to have the middle element equal to the target that I'm searching for. And of course, if that is the case, all I need to do is to return the index over here, since I'm going to also have indexes. And this is going to be a bit big, but you get the idea. Meaning that I say, if nums of the middle value that I have already found, and this is not a middle value, this is a middle index. If nums of middle index is actually equal to our target, all I'm going to do is return the middle index that I have already found. And the interesting part here is, how am I actually going to make the set bigger or smaller? I'm actually not making it bigger anytime, I'm just making it smaller all the time. But in order for me to make it small, I need to choose what kind of a subset I want included. So this I already explained, but I'm just going to go through it one more time. 1, 2, 3, 4, and 5. And let's say that I'm looking for the target is 5. I'm looking for the number 5. I'm going to take the middle and I'm going to say, is 3 less than 5? So if 5 is actually bigger than 3, then I'm going to look at the right, because I know that these are sorted. So everything on the right is going to be bigger. And if 5 is smaller than 3, I'm going to take a look at left. So that's pretty much it. All I need to do now is just increase or decrease high and low pointers. So that's pretty much it. On the other iterations, I'm going to get a new middle index here, because I have already increased or decreased low and high. Meaning that if nums of middle index is actually bigger than the target, all I need to do is to say high is going to be equal to middle index minus 1. And else low is going to be equal to middle index plus 1. So that's pretty much it. I'm actually going to remove the brackets so we can see it a bit clearer. And now you're going to get the whole idea. Once again, I'm going to draw it on the screen here, and I'm going to be looking for the number 5. I'm going to put it against 3. And now I'm going to say middle index is less than 3, right? So I'm not going to have this point. I'm going to go to the else. And here I'm going to just increase the low pointer. Low is going to come from here to here plus 1, meaning that I'm going to have the new low at this index. And of course, after that, I'm going to be looking at this set over here, 4 and 5, 4 and 5, and I'm going to have a new low and of course the old high. And that's pretty much it. That's all I need to do. The final part is, if I haven't found anything, it means that there is no target, and I have already got to a point where the target should be, because I already incremented the low pointer. And here at this stage, all I need to do is just to return low. And that's pretty much it. So let's actually say console, do the use example test cases, and run the code to see if this is going to be successful. Okay, we're still waiting, and there we go, accepted. Then I'm just going to push it to the server and hope for the best. And there it is. So it's running quite fast, even though I have already said don't look at these numbers, since they're not all the time correct. In fact, most of the time they're not correct. If you want to benchmark something, use benchmark.net, and that way you can see the exact runtime complexity and the exact speed. And that was binary search. Thank you for watching, and if you have any questions, leave them down below. Bye.